Today we are going to start a new topic, that is on waiting lines, which is also known as the queuing theory. Now, waiting lines or queuing theory, the first portion we shall have the introduction. First of all, let us know that almost everywhere we are having waiting lines or queues. One thing you see, particularly in country like ours, most of the situations are such that whether it is a railway counter or the bank counter, the number of arrivals or the people who come for service usually is very large compared to the rate of service. So, as a result, what happens that a steady state is not reached, right. So, if the steady state is not reached, then the kind of queuing theory that we are going to discuss is not very useful. So, it must be remembered that one of the first and foremost queuing theory requirement is that the service rate should be higher than the arrival rate. If the service rate is higher than arrival rate, then should there be any queue? The answer is usually it should not, but because there is a probability distribution both of the arrivals and also of the service, this probability distribution leads to formation of queue at a certain times, right, at certain times. So, that is the essential idea, that the foremost forbearing thing about the waiting lines or the queuing theory that we are talking about is that service rate should be higher than the arrival rate. Obviously, sometimes we find situations where there are multiple servers, that means queue may be single, but there are multiple servers. So, at that time all the service rate should be integrated, the total service rate should be found out, and that should be higher than the arrival rate. So, that is the basic requirement. This point will also come at an appropriate time, but let us begin now. So, as you can see here that waiting lines or queues, they are everywhere. The example could be found in banks, railway ticket counters, movie ticket counters, post offices and so on. And why should we study waiting lines or queues? Because it leads to tremendous loss of time. One example that I have taken from Hillier and Lieberman's book is the Americans lose nearly 20 million person years per year waiting in queues. So, all the examples which you saw just now, they are all about people waiting in banks, ticket counters, post offices and all. But apart from people, there are other kind of things that also wait. For example, the aeroplanes waiting for runway, machines waiting for repair, vehicles waiting in traffic jam, ships waiting in sea for entry into the port, right. Many of us do not know about the situation in port. What really happens, a very big queue actually forms, and sometimes the ships, the incoming ones, are not even they are given the go ahead to enter the port until unless the waiting ones are already served. So, all these are also leading to huge amount of the losses. So, the basic idea is about the queuing theory is the study of such waiting in different situations, and the queuing models determine how to operate a queuing system effectively, balancing on one side the social cost of waiting and the other side is the cost of providing service, right. So, obviously, if you do not want the people to wait, you have to spend more money in creating more service facilities. On the other side, if you spend too much on providing service, the queues will be less, but cost will be much higher. So, a balance or a trade off has to be obtained. So, that is the essential idea. Here are some more examples like ATM, bank, repair shop, vending machines, payment for purchase, all these are commercial situations. There are transport situations where there are cars, there are ship uploading, elevators, parking lot, or in business situations like material handling, health services, job shop, telecommunications. So, examples are many, and however, in all these situations a common thread runs that there is a queue that is formed, and which we shall show in our next diagram, that if you look at this particular diagram, there has to be an input source from which the customers come in, or you may say the customers are generated. Then there is a queuing system which basically includes a queue and a service mechanism. The queue where customers are waiting, usually we talk about a single queue that is formed, and we also assume an infinite length of the queue. Why will come later. Then that queuing system should have a service mechanism through which that people or the things are served, and there is also should be a queue discipline. What is that queue discipline? One example could be FCFS, first come first served. The first person who comes will be served, and finally the served customers, they are leaving the queuing system. So, that is the basic idea of a queuing process. Now, let us look at the details of the input source, or which is also sometimes called the calling population. See, usual assumption about the calling population or the input source is that it is infinite, but suppose it is not infinite, it is a finite source. See, moment it is a finite source, then you cannot really expect all the people to come with following an exact probability distribution. For example, the most commonly used probability distribution for modeling the arrivals in a queuing process is the so called Poisson distribution. The Poisson distribution assumption will not hold if the input source or the calling population is not infinite. So, you can see that if you think that there is a finite population, for example, let us look at a class. A class is having some 100 students, and all these students, after the class is over, they may be going to a coffee shop. So, these coffee shop, the input population is coming, most of the students are from the class. The class has a limited size. So, for some time you can have perhaps a Poisson approximation, but not for a longer period, because in that case, since the input population is limited, towards the end the assumption of Poisson distribution or a random or a Markovian process will not hold. So, these are the issues that must be remembered about the input source. You see, one thing that keep coming back, that if the number of arriving customers follow a Poisson distribution, which is basically a discrete distribution, probability distribution, and equivalence is the inter arrival time, which will be a continuous distribution, and it is exponential. So, there is an equivalence. This equivalence is of great importance, but we shall discuss this at an appropriate time. Now, while we talk about input source, there are certain other things which may be called as special cases that also should be remembered. The first one can be called balking. What is balking? The customers refuse to join a queue seeing its length. So, it is something like there is a highway, let us say the fuel station, where you are moving with your car and you see already quite a number of people are waiting. So, you are a customer, according to the theory, you have been generated, right? A customer is generated, but you do not join the queue seeing its length, it is quite long, and therefore, you go away. So, this can be called balking. The other process is jockeying. Jockeying is a process where suppose there are multiple queues and multiple servers, and one is like in normally you see in railway counters, one line is moving pretty fast, the other one is not moving so fast. So, what you do? You move from one queue to the other, right. So, a new customer is coming who is not generated in the usual process, it is coming from who have already joined in another part of the queue, that is called jockeying. There is a third one which is called reneging, when customers leave after spending some time in a queue before getting the service. So, you went for getting a railway ticket and you wait in the queue for some time and then you think it is too much, I will come back tomorrow, right. So, you go away, that is reneging. So, all these different cases can make the queuing system analysis more complicated, and we shall see some of them later on. The queue per se, as I have told you a few minutes back, it is characterized by the maximum number of customers that it can contain. It could be finite or infinite, but infinite assumption is more common. Why? Because moment you think a finite queue space, you are actually limiting the analysis, and moment you put a limit or a constant, your analysis will be that much more complicated. The next one is the queue discipline. The queue discipline, one very interesting thing about queue discipline is that the rule or what you call the order in which the customers are selected for service is not actually making the queue performance measures any different. So, it is something like this. Suppose you are waiting in front of a doctor, the doctor is following a peculiar queue discipline. What is that? Let us say last in first out. So, a last in first out means what? Means the patient who comes last goes to the doctor first. Now, it is not something very good or usual, you do not like it. As a patient, you might have come the first thing in the morning, you are waiting for long, and another customer or another patient who comes at the last moment goes before you, you do not like it. So, but what about the doctor? You look at the doctor, to the doctor every patient is the same. If the doctor is seeing, let us say 10 patients per hour, that rate remains same, or in fact, if the patients or the other people do not tell the doctor will not even know that the people are not happy because of the queue discipline. So, queue discipline is something which is very important to the customers, but not important as far as the queue performance is concerned. So, you see all these points come if there are people. Suppose there are not people, suppose these are actually jobs, the jobs do not think. Since jobs do not think, it really does not matter whether it is FCFS or last in first out or random order or something else. So, therefore, the queue discipline is important at a certain point of time. Obviously, even for jobs it may matter. Suppose there is something like the jobs must maintain a certain temperature. So, if you follow last in first out like in stacking, what will happen there? The job that has come before might have already lost heat by the time it goes in. So, that is not something good. So, queue discipline is an important consideration, but unfortunately, most of the queuing performance measures do not change because of queue discipline, right. What is the impact of queue discipline? We shall again look into later. Then, like the customer is generated, there is an arrival pattern, there is also a service mechanism. The service mechanism consists one or more parallel service channels known as servers, right, and the service time is usually assumed to be exponential, right, or exponentially distributed. Other important service time distribution could be like degenerate distribution, which is a constant service time, or it could be Erlang or gamma distribution. So, there could be many other distribution as well. So, these are some common distributions which are important in the context of the queue. So, here is an elementary queuing process. If you see that there is an input source, the customers are coming from the input source and they are waiting in the queue, and in the service utility there are 3 servers, right. So, from this common queue the customers are joining one of the servers and thereafter getting their service, and after the service is over the served customers are leaving the system. So, once again very quickly the queuing process is that there are customers which could be people like people waiting in bank, or it could be jobs, or it could be aircrafts waiting for runway, or it could be trains waiting for getting into the station, it could be a car in a traffic jam, whatever the case may be, it has to be generated. The customer is generated through a process and that depends on what is the source, input source or the calling population, right. A probability distribution has to be there. Then it joins a queue. Most typical assumption of the queue is it's a infinite queue length, right. Then there is a queuing system. The queuing system basically means the queue plus the service utility, right. So, there are some queue characteristics and there are some system characteristics. Usually we do not use the queuing system word all the time, we simply say system. When we say system, we should basically mean queuing system, right. So, there are queue utilities, there are system utilities. The queue utilities refer to the like LQ, the number of average number of customers they are in the queue, that is L, right. Whereas LQ, the L is on the other side is the total number of customers there in the queuing system. So, what is the difference between L and LQ? L stands for the number of customers in the queuing system and LQ stands for the number of customers in the queue. So, L equal to LQ plus number of customers in service, average number of customers in service. So, right. So, these are the things, and finally, the served customers leave the system. Sometimes there could be situations where the served customers are also waiting in the queuing system, then the system becomes more complex and analysis will be that much more difficult. This point I have already told that there is a key requirement. What is that key requirement? That arrival rate should be less than the service rate, right. So, all the queuing relations are derived in the steady state. What is steady state? Steady state means that the system has come to an equilibrium. Usually what happens that whenever a queuing system begins, there is a transitory period. For some time before it comes to a steady state, assuming that arrival rate is less than service rate, till such time all the queue related parameters are not having stable values, but after some time they reach steady state and all the queue related parameters they achieve stable values, right. So, the kind of queuing system that we are going to discuss, they are all having this particular requirement that an service rate is higher than the arrival rate, a steady state is reached, and after steady state is reached all the queue parameters are then considered. As I already said before, for multiple servers the combined service rate should be considered, not rare, it should be rate, combined service rate should be considered. Now, I was talking about different performance measures. What are these performance measures? Let us look at P0, the first performance measure, it means probability that there are no customers in the system. Pn, probability that there are n customers in the system. L, average number of customers in the system. LQ, average number of customers in the queue. W, average time a customer spends in the system, and WQ, average time a customer spends in the queue. Finally, there is parameter called rho, which is utilization rate for each server, or in other words the percentage of time that each server is busy. So, just let us look at this once again, that supposing this is my queuing system. this is my queuing system. So, this is the input source. Customers are generated and they are joining the queue here, right, and then they go to this service utility and then from here the served customers go away, and this one is the arriving customer. So, let us look at the usual thing. The arriving customers are generated in the Poisson process, right. The service utility or the service system, or to be more precise, the service time is exponential. Not that it cannot be anything else, but this is the most common assumption. So, here these arriving customers join the queue, and after that they get service. Let us say there are 2 servers. So, 2 are in service and then they go away. Now, it does not mean that 2 will be in service all the time. Suppose there is nobody in the queue and there is in the system only one person. When there is only one person, there will be only one person in the service, nobody in the queue, right. So, this could be a situation. Suppose there is nobody in the queue and nobody in the service, then the system is idle. There is nobody in the queue, there is nobody in the service. But other situations, there could be nobody in the queue, but there could be 2 people in the service, that is also possible, right. So, all these different combinations are possible. Now, this portion is the queue, right. So, when we talk about measures such as LQ and WQ, right, LQ is the number of customers in queue and WQ is waiting time in queue, right. So, this is LQ and WQ, they refer to the queue, whereas L and W they refer to the system. So, these are number of customers in system. System means queuing system, and W waiting time. Obviously, all of these are average waiting time in system, right. So, these fine differences must be understood. Please understand that all LQ, WQ, L, W, they all are calculated after the system has come to a steady state, right. The system has to come to a steady state, then a fixed value of all these performance measures would be obtained, and then the average value of this, because number of customers are changing all the time, right, all the time. What is their average values, all right. So, all of this. So, what when I say steady state, I basically mean that average values has come to a steady state, right. So, after we look at these steady state performance measures, is there any relationship that actually relates this variable one to the other, right. Fortunately, there are, and this formula is called the Little's formula. Like there are Little's formulas which actually relate the L and W and LQ and W. So, look at these are the relations, that L equal to lambda bar W and LQ equal to lambda bar WQ, right. So, these are Little's formula, and fortunately for us, these formulas are quite robust. What is meant by quite robust? That means that these formulas are applicable across a large number of queuing systems. These formulas are applicable. So, how does it help us? See, lambda bar usually is, what is lambda? Obviously, I have not said. The lambda is the customer's arriving rate, right. So, arrival number of customers per unit time, that can be called as lambda. Now, you see the lambda could be constant most of the time. Suppose we assume it is a perfect Poisson process, then lambda is nothing but lambda bar. The number of arrivals are on the in the average number of customers, they are same all the time. Sometimes, but then if the process is not really Poisson for some time, right. Let us say for initial period nobody comes, after 10 minutes people start arriving, then obviously the lambda bar has to be an average lambdas of all that is considered. That is why it is not lambda really, it is lambda bar. So, what is lambda bar? Lambda bar is average value of the lambdas or average arrival rates, right. In fact, individual lambdas are also averages, please remember this. So, it is more like average of the averages, average of a particular time. Anyhow, so that is how they are actually related, that is L and LQ. Derived formula sometimes also is useful, that is W equal to WQ plus 1 by mu, right. So, this we shall see at an appropriate time, that if we know only one steady state parameter out of the 4, that is L, LQ, W, WQ, using Little's formula we can find out all the other 3. Suppose you only know L, lambda is known anyway, then we can find W. Suppose you know only LQ, then you can find WQ, from WQ you can find W, from W you can find L, right. So, these Little's formula are very important ones. I am not really showing their derivation and how they have come, but let us take that these formulas are available, are very important formulas, and these formulas help us to obtain the steady state parameters of a queuing system. If we somehow can calculate one of them, particularly which one, the formula for which is the simplest. Suppose the L formula is simplest, compute L, W formula is simplest, compute W, right. So, if you can compute only one of them, you can get all the other 3 by using Little's formula. So, please remember Little's formula are very important, and not only that, they are quite robust, that means they are applicable in many different queuing situations, right. To summarize the characteristics of the queuing system, 6 parameters in shorthand, like it is written A, B, then C, then D, E and F. A is the arrival distribution, let us say Poisson. B is the service distribution, right, that is maybe Poisson, departure or service rate, in other words exponential service time. C is the number of servers, 1, 2 to infinity. D is the service discipline, like FCFS, last in first out, service in random order. E is the maximum number allowed in the system, right, infinite or finite, and F is the size of input source, right. One example of Kendall's notation. So, let us look at MM1 FCFS infinity infinity, right. Now, that this classification is M is the arrival process is Markovian. Markovian means either Poisson or exponential. So, arrival process is Poisson, number of arrivals is Poisson, inter arrival time is exponential, service time is exponential, or the number of service which is normally not used, that is what is known as Poisson. Number of servers 1 because MM1. Then FCFS is the queue discipline, that is the first come first serve. The system size is infinity, infinite waiting lines, that means the queue length is infinite, and then last infinity is population size, that means the input population size or the calling population size. Then notation M stands for Poisson arrival or exponential service time, right. Now, there could be others like deterministic, constant arrival rate or service time, or G for general, right, general probability for arrival or service time. So, this is about introduction. We stop here, and from our next class we see in details. Thank you.